Today I'm going to teach you about direct and indirect or inverse variation. And we have already discussed direct in the past. It is y equals kx. The only difference is that now we may have power on it since we are studying polynomial and rational functions. So our first problem today says, suppose t varies directly to x to the 1/5. Varies directly is our key words. Those would be our verbs. So we would have t equals k times x to the 1.5. Now we can substitute in 4 for x and 20 for t to solve for our constant of variation. So 20 equals k times 4 to the 1.5. That's 20 equals k times 8 divided by 8. Let's see, 4 goes into both those, so we get 5 halves. So k is 5 halves, or 2.5. So our equation of variation, we then take that k value and plug it in. So we would get t equals 2.5 times x to the 1.5. Once you write your equation of variation, you can then continue to substitute. T would equal 2.5 times 16 to the 1.5. So if you would punch that in your calculators, you should get 160. And again, that's direct variation when you multiply. So if I multiply with direct variation, when I would do indirect or inverse variation, I would have to divide. So this reads y varies inversely with x. So then that becomes y equals k divided by x. And we are not sure of our power of n. So we are going to have to try different ones. So first, if we substitute into this equation, we would get y equals k, let's try 1. So in the y spot, we would put 4 equals k divided by 1. If I do my cross products, I get k equals 4. Let's try the next one. 1 equals k divided by 2. Cross products, I get k equals 2. These k's are not constant, so we know it can't be a power of 1. So then we would try a power of 2. And we would get 4 equals k divided by 1 squared. That's 4 equals k divided by 1. That's k equals 4. Try the next one. 1 equals k divided by 2 squared. That's 1 equals k divided by 4. Cross products, I get k is 4. So this is looking like a constant. Let's try our next one. 4/9 equals k divided by 3 squared. That is 4/9 equals k divided by 9. If I do my cross products, I get 36 equals 9k divided by 9, and k is 4. So I did find a constant of variation every time where k was 4. So that means my equation would read y equals 4 divided by x squared, where k is 4 and my n, my power on my x, would have been 2. Now I'd like to talk to you about polynomial versus rational inequalities. Remember, if something was polynomial, it was an expression where everything was added or subtracted and all the powers were whole numbers. Where if it was rational, it was one polynomial divided by another. When we are solving either of these, we will be asked to find 3 different things. We will first be asked to find where the function equals 0, and if it ends up being rational, we could also state where the function is undefined because we have asymptotes. So if our function isn't equal to 0, for inequality it would be greater than 0, so we'll find the places where it's greater than 0, or less than 0. So we will have different problems like this. If on this first one I have this graph, is it a polynomial graph or a rational graph? Polynomial, since there are 1, 2, 3 turning points. So if it's polynomial, we can just look at the graph and say, where does it equal 0? Well, here's where y is 0. So what x values, what domain makes this y value 0? It looks like we have x equals -4, x equals -3, x equals 0, and x equals 1. Our next question then is going to ask, where is the function greater than 0? Well, greater than 0 would be above this y equals 0. So that occurs here, here, and here. And it is just greater than. There is no equal bar. So then that means out here is -infinity to -4, union 3 to 0, union 1 to positive infinity. All of those should give us greater than 0. And last, it will ask us, where is the function less than 0? Less than 0 means below the y equals 0 line. So that occurs here and here. So it occurs between -4 and -3, union 0 and 1. This next graph, is it a polynomial graph or is it a rational graph? It is a rational graph because it is a hyperbola and we have asymptotes. So if we have asymptotes, not only can we see if the graph ever becomes 0, but we can also say where it is undefined. So first, the blue graph is 0 at this point 0. It is undefined at x equals 2. It is also undefined at y equals 1. Next, we have, where does the function go greater than 0? So again, that would be above the y equals 0. It looks like all of this, and this piece is above this line y equals 0. So that looks like it occurs out here at negative infinity, 2, 1, union 2 to positive infinity. Now notice the asymptote is at 2, and by us putting a parenthesis, we definitely know it is not 2, but beyond 2. If this were an equal bar, this would be still a, if it were equal, this would be a bracket at 0 because I am equal there, but it would be an open parenthesis at 2 because I never actually get to 2, but I am beyond it. And our last one is where is the function less than 0? So that's below this line, y equals 0. And that occurs right here. So that looks like it is occurring from 0 to 2. So that is looking at a graph and interpreting those things. What if it asks us to solve it symbolically? Symbolically means do your algebra. And notice all of these are polynomials on this page. So when you have polynomials, you want to get it set equal to 0, and then you want to factor. So if we solve, this first one is compared to 0. So we just now need to factor. What's common to both? An x. So that leaves x squared minus 1. This part still factors further. So I have my x, and I have x and x, 1 and 1, a plus and a minus. So my actual zeros happen at x equals 0, at x equals negative 1, and at x equals 1. Those are my actual zeros. So again, I'm going to use my line graph to list those actual zeros. I would have a negative 1, a 0, and a 1. 0 was a 0. Left of zeros are my negative factors. Right are my positive factors. Negative 1 was a 0. Left of a 0 are negative factors. Right of it are positive factors. 1 was a 0. Left of it are negative factors. Right of it are positive factors. That now breaks it into 1, 2, 3, 4 sets of zeros. Notice we had all these factors multiplied together. What is a negative times a negative times a negative? That would be a negative. A negative times a positive times a negative. That would be a positive. A negative times a positive times a positive would be a negative. And a positive times a positive times a positive should be a positive. Then I look at my inequality. Greater than 0 are our positive numbers. Our positive numbers occurred in here and out here. And it is just a greater than, so it is from negative 1 to 0, union 1 to positive infinity. So let's go ahead and try another one. X to the 4th minus 13x squared plus 36 is less than or equal to 0. Again, it's a trinomial compared to 0, so I should be able to right away factor. What would we do with x to the 4th? X squared and x squared. The factors of 36, that add up to 13. 9 and 4. Some, same sign, so both must be negative. This factors further. X minus 3 x plus 3. This also factors further to x minus 2, x plus 2. So here I get an actual 0 at 3. Here a 0 at negative 3. Here a 0 at 2. And here a 0 at negative 2. So again, on my number line, I'm going to put these in order. Be a negative 3, a negative 2, a 2, and a 3. These were zeros. Left is negative, right are positives. 0. Left is negative, right are positives. This was a 0. Left are negatives, right are positives. And this was a 0. Left are negatives, right are positives. So that breaks it into 1, 2, 3, 4, 5 sets of factors. And again, I'm multiplying all my factors. Negative, 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 negative make a positive. Negative, 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 positive are a negative. Negative, negative, positive, positive are a positive. Negative, positive, positive are a negative. And all positives make a positive. This time I am looking for all the factors that are less than or equal to 0. Less than 0 are our negative factors. But now I have the equal bar, so I'm going to use the brace. Negatives happen in here, and negatives happen in here. So this is from negative 3 to negative 2, union 2 to 3. And let's try one last polynomial. And this one is not equal to 0. So we're going to have to solve it so we compare it to 0. So we have 2x cubed. We would subtract the 3x squared. We would subtract the 5x. And then we would have 0 on that side. We should now be able to factor. There is an x in every one of them. So this gives me 2x squared minus 3x minus 5. This part should factor further. So I have 2x and x. My only factors of 5 are 5 and 1. Inside here is 5x. Outside here is 2x. To differ by a negative 3, the 5 needs to be negative and the 2 positive. So here I get an actual 0 of 0. Here I get a 0 of 5 halves. Here I get a 0 of negative 1. So again, on my number line, I would have a negative 1, a 0, and a 5 halves. Negative 1 was a 0. Left are negatives, right are positives. 0 was a 0, left are negatives, right are positives. 5 halves was a 0, left are negatives, right are positives. 1, 2, 3, 4 sets of factors. 3 negatives make a negative, 2 negatives and a positive are a positive, a negative, and a positive. This time I am looking for the factors less than 0. Those would be my negative factors. They occur out here and in between here. So from negative infinity to negative 1, union 0 to 5 halves. That is the polynomial inequalities. Now let's look at the rational inequalities. First of all, when you have a rational inequality, you must make sure it is rational. One polynomial over another polynomial. And then you will do the same thing and compare it to 0. You will then find what are called its boundaries. You will do that by taking the numerator and setting it equal to 0, and the denominator and setting it equal to 0. Once you've determined your boundaries, you will then set up your intervals just like you did with your polynomials, and we will use the table feature of our calculator to check where it's positive and where it's negative. So here is our first polynomial. 3 minus 2x divided by 1 plus x is less than 0. This is one polynomial divided by another polynomial, so we are already in this rational form. In the numerator, I have 3 minus 2x, so I am going to solve that for 0, and I get x equals 3 halves. In the denominator, I have 1 plus x, so I'm going to solve that for 0, and I get x equals negative 1. So then on my number line, I'm going to place those. A negative 1 is to the left of a 3 halves. So I have values I'm going to look at from negative infinity to 1, between negative 1 and 3 halves, and between 3 halves to positive infinity. And I am looking for where it's negative. So this is where you'll now get your calculator, and we will put our function in our calculator. And our function is, in parentheses, 3 minus 2x divided by, in parentheses, x plus 1. And enter that. Now, if we go to our table, we will not see halves unless we set our table change to halves. So let's go to our table set, and we can start at negative 3, but to see these halves, I'm going to have to change my table set to halves. So I'm going to put change table to 0.5. So now I can go to my table. From negative to negative 1, look at your y values. You get negative values. So I'm going to put a negative in here. At negative 1, we get an error. That's because that was our asymptote. It was our denominator. So this should be an error. From negative 1 to 1.5. So we're going to scroll down the table. Right here, this is looking like our y values are positive numbers. So I'm going to put a positive in here. Notice when we got to 1.5, we had an actual 0. That's because that was in the numerator. Now I need to look beyond 1.5. What kind of values am I getting? Negative values. So again, because I am looking for less than 0, those would be my negative values. They occur here, and they occur here. So that is from negative infinity to negative 1, union 3 halves to positive infinity. Okay, let's try another one. 2 minus 5 divide x plus 2 divide x squared is greater than or equal to 0. As it stands right now, this is not one polynomial over another. So to get it to be one polynomial, I'm going to have to change these to common factors of x squared. So I would have to multiply this one by x squared over x squared. To get this to be x squared, I'm going to have to multiply by x and by x. This already reads a x squared. So then I get 2x squared minus 5x plus 2 in my numerator. and my denominator is all x squared. So then, if I factor my numerator, I get 2x minus 1 times x minus 2 all over x squared. So now I can actually find my boundaries. And my boundaries here occur at 1/2, at 2, and at 0. So again, I'm going to put those on a number line. 0, then would be 1/2, then would be 2. I'm going to enter that in my calculator in y equals. I'm going to enter my extended polynomial. So clear this one out. So parentheses 2x squared minus 5x plus 2. Parenthesis divided by, and close your denominator in parentheses, x squared. So again, I'm going to have to check. But between 0 and 1/2, if I count by halves, I'm not going to have any values. So maybe here's where I want to change it to fourths. So I'm going to go to my table set. And I'm going to have to start left of 0. So let's start at -1. And maybe I want to count by fourths, or maybe I want to count by tenths. If I do fourths, that would be 0.25. I would at least get a value in between 0 and 1/2. And let's go to our table. Left of 0. Here's my 0. Again, that was an error because that was my denominator, so that was an asymptote. These two boundaries came from my numerator, so those should be zeros. So left of 0 would be all these values. Those values are all positive, so I'm going to record that. Between 0 and 1/2 is also a positive value. At 1/2, I have a 0. Between 1/2 and 2, those are all negative values. At 2, I do get my 0 because that came from a numerator. And beyond 2, I'm getting positive numbers. This time I'm asking for where is the function greater than or equal to 0. Greater than 0 would be positives. Equal would be where it exactly hits 0. So here are my positives, here and here. This is an error, so I can never get there, so I can never equal that. But on this side of it, I then have positives again and equal to a 0. Then I have positives out here and a 0. So that is -infinity to 0, union 0 to positive infinity, positive 1/2, inclusive, union 2 to positive infinity. I can't just say -infinity to 1/2 because I have that asymptote in there, so that would include the 0 unless I write it with the parentheses. That should be enough for you to get started on your problems.